Alright, today we're going to be focusing on exponential functions, how to write one, basically how to create an equation given some given situation or scenario. The main things to focus on is being able to define and explain properties of these exponential functions. So we have this thing called a growth factor we've talked about. There's something called decay and depreciation. We also have this new word, principal, and it's essentially just another way of saying my initial value, whatever amount I'm starting with. We did that zombie project a few classes ago, and that initial amount of zombies was our principal value. So we'll be working with that a lot today. Just to review, go ahead and ask yourself a question. Which of these graphs shows an exponential function? Not a linear function, an exponential. Is it this one over here, or is it this one right here? If you chose A, you are in fact correct, because this is my exponential function where I have a curved graph. Anytime I have that perfectly straight line, that is actually linear, not exponential. And we will be focusing on these exponential functions for the rest of our unit. If you were to look at these two different equations, and we talked about this last class as well, one of these is for linear equation, but the other one is my exponential function equation. And if you were to guess on your own, hopefully you answered that this is my exponential function equation. When I have that x in the exponent spot, that is my sign that this is an exponential function, whereas this one is for my linear functions, my y equals mx plus b, the stuff that you kind of studied in middle school. But we are going to be focusing on exponential functions. So now let's get into kind of the main portion of today. Let's look at this given situation. There's pretend you are a population geneticist, so someone who studies the population of animals, counts them, keeps track of their population. Are they growing? Are they becoming extinct? Are they endangered? That sort of a thing. You are a population geneticist, and the number of narwhals in your area is dropping to 1/3 of its population every year. If the population is currently at 1,000 narwhals, how many will be there? How many will be there in 5 years? So we have this decreasing narwhal population. We want to know how many are going to be left after 5 years. Let's go ahead, before we even start working specifically with the problem, let's review kind of what our exponential equation looks like and what each of those pieces represents. So we're using this exponential equation, y equals a times b to the x. The a is my initial amount, otherwise known as principal. So my principal value. And my b is something that we are calling the growth factor. Sometimes, though, we are decreasing. So just like this one, it's actually going to be my decay factor. Growth or decay. So what I'm growing by, what am I multiplying by over and over again? Or, in other words, what am I dividing by over and over again in this situation? The third part of this equation, which we don't always reference every single time, but usually this x represents time. It could represent a couple other things, but for our situation, it is representing time. So let's go ahead and fill in these spots in my equation with the information from my given situation. So I have y equals a times b to the x. And my a, like I said before, that's my initial amount, my principal amount. The principal amount in this scenario is talking about my number of narwhals. My original number of narwhals is 1,000. So when I'm writing this equation, I'm going to write y equals 1,000. My growth or decay factor, it's asking what am I growing or what am I multiplying or dividing by? And well, if you look at the population of the narwhals, it is dropping to 1/3 of its population every year. So we are going to be multiplying times 1/3 every single time. So 1/3 is going to be the base in my exponent. And the last part it's asking is, well, how many narwhals are going to be there in 5 years? My x, my time, how many are going to be there in 5 years? So for that equation, I'm going to put a 5 up in the exponent spot. And all I have to do then is essentially plug this into my calculator. When you are plugging this into your calculator, make sure that you are first going to plug in this part of your equation, that 1/3 to the 5th power. So you're taking 1/3 times itself 5 times. 1/3 times 1/3 times 1/3 times 1/3 times 1/3. Go ahead and take a second and see if you can plug that into your calculator. You're going to get a really, really small decimal, but you're going to then multiply it times 1,000, in which we will get a final answer of y equals 4.12 narwhals. We started off with a population of 1,000 narwhals, and we have dropped down to a total of 4.12 narwhals after 5 years. That is a huge, 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 huge decrease. And it's because we're exponentially decaying. We're growing really, really small. We're dividing over and over and over again until we're left with only 4 narwhals in this area. Huge decrease, but that's what happens when we have exponential decay. Sometimes our growth factor isn't as straightforward as this 1/3 situation where I know exactly what I'm dividing by over and over again. Other times, I have a growth or decay factor that's a percentage. When we have this situation, we are going to go through something slightly different, a different process to figure out what that b in my a times b to the x equation is, my growth or decay factor. So this is specifically for when I have percentages. If I have a percentage, it says 50% of the apple trees in Wisconsin die every year. If I have a percentage, what we're going to do is we're going to take 1 plus that percentage if I am growing, or I'm going to take 1 minus that percentage if I am decaying. And when I'm talking about using that percentage, I'm talking about the decimal version of that percentage. So for instance, when I'm talking about 50% of the apple trees in Wisconsin die every year, I'm talking specifically about decay. Dying means decay. I'm going to get less and less and less. And if I'm going to have 50%, if I write 50% as a decimal, I'm moving the decimal point 2 places to the left and putting it right there. So 50% as a decimal is the same thing as 0.5. So I'm going to take 1 minus 0.5, and I'm going to get my b equals 0.5. That's going to go into my equation, my b part of my equation. Question number 2 says the population of velociraptors is in the area is increasing by 15% yearly. So I'm going to take 15% as a decimal, which is 0.15. I'm going to take 1 plus 0.15 because I'm growing, I'm increasing, and that means my b value is 1.15. For number 3, the number of people who sing in the shower increases by 60% every year. So I'm going to take 1 plus 0.60, which equals 1.6. That will be my b value. And question number 4, the number of people who can do a backflip decreases by 20% every year. So decrease, I'm decaying, so I'm going to subtract from 1 now. I'm going to take 1 minus 0.20, and 1 minus 0.20 is 0.80. And that will be my b factor. That's what's going to go into the b part of my equation. Anytime I have a percentage, I'm going to do this 1 plus that percent or 1 minus that percent in order to find the growth or decay factor for my equation. So today's goal was to be able to identify and calculate certain components of exponential functions. So this goal right here. And we went over growth factor and decay and growth, as well as what principal means. So hopefully by the end of today we can check off all of those parts of our scale. We are still working on level 2. We should be finishing up that level 2 stuff by hopefully the end of next week.